So now I want to talk about the alternating series test. So alternating series, what I mean when I say alternating, the thing that alternates is the sign. Now this can come in a couple of different versions, but typically what you'll see is a -1 coefficient, right, in parentheses, and then it'll have an exponent, either an n plus 1, n minus 1, something like that. Okay? So let's just write out what this is going to look like in this case, where I have a -1 to the n times this a sub n, this general term. So if n equals 1, I have -1 to the 1. That makes it negative. So I'll have a -1 times a sub 1. Right? Now when n is 2, I'll have -1 squared. That'll make that +1. So then it'll be plus a sub 2. For n equals 3, I'm back to negative a sub 3, right? And now you see the pattern, right? So we're just going to alternate our signs between plus and minus. Okay? So here's how the alternating series test works. It's actually one of the easier ones to do. So if the limit as n gets big of a sub n, so without the plus or minus 1, so if just like the absolute value of each of those terms goes to 0, right, gets progressively smaller, then the alternating series, right, we say converges. And I'm going to qualify that. So it's kind of like converges asterisk conditionally. Now, some books, some homework systems are going to say, well, if it converges conditionally, then it converges. Because that's really, right, the actual series is with the alternating sign. So if it converges, right? You'll just want to check and see what works for the homework system you're using. Now, if the series would converge even if you took out the plus or minus. So if I just took the absolute value of each of these terms and added them up, if that series would converge, then we would say that the alternating series, notice I put the -1 in there again, then this would converge absolutely. I think absolute value, right? So it really, really converges. Okay. Now finally, if that nth term in your series does not go to 0, then the alternating series, right, it doesn't matter. We say that this diverges. Right? So it's just swinging wildly back and forth, big plus, big minuses. Okay? All right, so let's look at some partial sums so we can kind of get a handle on this and maybe convince yourself, oh, okay, that makes sense. Okay? So look at the partial sum. So I've changed it up just a little bit. I have a -1 to the n plus 1, right, times a sub n. Let's just think about what those partial sums are going to be. So actually, maybe let's write above this. I'll write out a few of these terms here. So it would be, so if n is 1, that's positive. We're going to start positive this time. So positive a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus, right, and it keeps going. Okay, so s sub 1, your first partial sum, that's just your first term. Your next partial sum, right, a sub 1 minus a sub 2, right, you add the first two together. Okay. A sub 3, right, you just add those first three terms together. That was supposed to be 2 plus a sub 3. Okay. A sub 1 minus a sub 2 plus a sub 3 minus a sub 4. Okay, so you can see we're kind of bouncing back and forth. So what that looks like graphically, so if it's going to converge, right, so if this alternating series converges, then there exists some sum s, right? It's going to come out to be some value of s. Well, look what happens when we start plotting those partial sums, right? So in this particular case, right, that first one that we get is going to be above our sum, right? Now, the next thing that happens is we subtract off a sub 2. So s sub 2, we're going to take our s sub 1 and we're going to subtract off a sub 2. So here's that, right, difference is a sub 2. Well, the next thing we do is, right, we add. So we're going to go back up above, right? So when we get to s sub 3, we're going to add on that a sub 3 value. So it's going to go above. But remember, right, we're saying it converges. That means each of these a sub i's coming after are smaller. So we're going to go back, but we're not going to go back as far. So a sub 3, right, that step is less than our a sub 2 step, which was less than our big first a sub 1 step. So as you can imagine, right, these partial sums are just going to get progressively smaller around that actual sum of the infinite series. So that's why we can have this alternating series converging. Oops, sorry about that. Okay, so let's do some examples. Practice, as I like to say. So let's determine if the following series converge, either conditionally or absolutely, or if they diverge. Okay, so we can write out the first couple of terms just so we sort of see what it looks like. So if n is 1, I'm going to get negative 1 over 1.1, and then the next one is positive 1 over 1.1 squared, and then negative 1 over 1.1 cubed, etc. Okay, so alternating series, great. So we can check for conditional convergence, right? So we are only looking to see if 1 over 1.1 to the n, so without the alternating part, if this nth term, as n gets big, does that go to 0, right? And it does, as long as your denominator is greater than 1, right? This goes to 0. And I want to say p series, but I use p series for something else. I guess we'll call it p series. Okay, so p is greater than 1. So the limit of 1 over 1.1 to the n as n goes to infinity is 0. So therefore, right, this converges. Now, does it converge conditionally or absolutely? Okay. Well, right, in this case, it's going to converge absolutely because, again, it's this p series where, right, if I just had the series 1 over 1.1 to the n, right, this series would converge. Again, p series. I guess it is p series. P series, and my p is greater than 1, right? 1.1 is greater than 1. So it converges without the absolute or without the alternating part, so it converges with the alternating part, and it converges absolutely. If you don't put the absolutely on there, that's totally fine as well. Okay, let's look at the next one. So this is the other way that you can get the signs to change. You can do it instead of with the negative 1 to a power, a cosine or a sine with an n pi or some version of that. All right, and you can see, let's just write out the first couple of terms. So if n equals 1, I have the cosine of pi, which is negative 1, over n, which is 1. And then the next one, if n is 2, I have the cosine of 2 pi, so that's plus 1 over n, 2. Now we're at n equals 3, so cosine of 3 pi, that's minus 1 over 3. Okay, there's the pattern, plus 1/4, etc. Okay. So negative 1 plus 1/2 minus 1/3 plus 1/4. Okay, so we have an alternating series, so we're taking a look at does the limit of the nth term, what is the limit as n gets big? Okay. Well, your numerator is just bouncing back and forth between plus and minus 1, right? But your denominator is getting big without bound. So that does equal 0. So nth term, right, goes to 0. So its alternating series test tells me that the alternating series converges. Okay. Now for this one, it actually converges just conditionally. And I shouldn't caveat like that. So not just. It converges conditionally. Meaning this series converges, but if I took out the alternating part, the series just 1 over n diverges. That's our harmonic series, and it does not get to 0 fast enough. So this one diverges. So I can't say that the series I have converges absolutely. It only converges with that cosine and pi there. Okay. Okay, I'll stop there. This is the harmonic series is what I said. Harmonic series. Okay, last one. So I have an alternating series, n to the 4th over n cubed plus n squared plus 3. You know what I'm getting at, right? So we're going to look at the limit as n gets big of just that nth term. So I take out the alternating part. Does this go to 0? if it does, then right, we converge at least conditionally. So as n gets big, well, how did we do this before? I could divide through everybody by n cubed. So then it's the limit of n over 1 plus 1 over n plus 1 over, or 3 over n cubed. And we're taking the limit as n goes to infinity. So then I'm going to get infinity on the top. I'm going to get a 1. I'm going to get a plus a 0 and plus a 0. So I'm going to get infinity over 1. So I'll get infinity. That is not 0. My terms are not getting smaller. So then this actually diverges from the divergent test or the nth term test, whatever word you're going to use for that.